So this is just the background review for neurophysiology. So you have to know a little bit of knowledge for physics too, so let's just go over some basic stuff, like electric charge and electric force. Why this is important is there are sodium ions, potassium ions. These are electric charges inside and outside the solution of a neuron. So that's why we're talking about electric force. So some basic stuff, like charges repel each other. So a positive charge will repel another positive charge. A negative charge will repel a negative charge. And the closer the charges, the stronger the force. And this is demonstrated by this equation. F equals K, Q1, Q2. The Q's just stand for the charge over R squared. So I just want to show you what happens for different distances for the forces, right? So you don't have to worry about the stuff on the top, just worry about this ratio, right? So it shows that F equals 1 over R squared. So if you have two objects, right, that are distance apart, and let's say the radius for this is 4, and the radius for this one is 2. I know that the radius is like from half the length, so just keep that in mind. So F equals 1 over R squared, right? Let's just assume 4 is the radius and put it in. So that becomes F equals 1 over 16, right? Do the same thing for over here. So when the two charges are closer to each other, F equals 1 over 2 squared, you get F equals 1 over 4. So as you can see, F equals 1 over 4 is a lot bigger than 1 over 16, 0.0625. So this just shows that the closer two charges are to each other, the stronger the force. And that's the main takeaway I want you to take from just this equation. And just another fact, charge is measured in coulombs. These are the units will be handy later on. So just moving on to a bunch of definitions, current is equal to the movement of charge per unit of time. For example, the current of sodium ions coming into a neuron, that's current, and then the units are measured in amperes. It stands for an A, like the units are in A. Voltage, the difference in electric potential per unit charge between 2 points. Voltage, you can use the V to stand for voltage. Resistance, the opposition to the passage of an electric current through a medium. Ohms, it's represented by this sign. Capacitance, the amount of electric potential stored, of energy stored or separated for a given electric potential, and that's in farads, F. And then conductance, the ease of flow of current between 2 points, and it's a S. So moving on, we have Ohm's Law, right? So the flow of current is equal to the electric pressure voltage over the resistance to current flow. So that might sound complicated, but it's just flow of current, right? Flow of current. You can represent that as an I. So I know, like over here, the units are in amperes, but in this situation and in IV plots in neurophysiology, current can be represented as I. And then is equal, so equal sign, to the electric pressure. So electric pressure is just voltage, so V, over the resistance, so divided by R. And I know, once again, that resistance over here, it's represented by ohms in this symbol, but once again, in IV plots, in neurophysiology, you can represent resistance as R. And then this is the same thing, it's just Ohm's law in a different way. Voltage is equal to, so V equals equal sign, to current times resistance, so I times R. So moving on, so that was just the physics part, and now let's talk about diffusion. Diffusion leads to movement from high concentration to low concentration, resulting in even distribution throughout the medium. So it's just a product of nature that everything wants to be equal, and so it creates this tendency to be always try to be equal. So as demonstrated in this example, we have a high amount of particles on one side that can pass through a permeable layer right here, and so stuff from the high side wants to go over here because there's too much on one side, and so a little bit starts coming over, and then finally you'll have an even mixture on both sides. So going on that topic, isotonic means the same solution concentration on either side. Hypertonic is higher solute concentration, and hypotonic is lower solute concentration. Remember, they have to specify, or they have to give you an assumption that what they're talking about, right? So in this case, it's pretty clear that both of these are isotonic to each other, because there's both 6 inside and outside, right? But over here, I mean, if they give you a picture, then it's very clear which one's hypertonic. But they have to give you a frame of reference, right? Otherwise, it'd be kind of confusing. So, for example, in this example, I can say that I placed a bag, right? I placed a bag of particles inside a hypertonic solution, meaning that this bag has less particles than the stuff that I'm putting it in. So I'm placing a bag into a hypertonic solution because the hypertonic solution has more particles than what is inside the bag. And what happens is, just like in the diffusion, everything has a tendency to go from high to low. And so since there's a higher particle concentration inside, it will go, outside, it will go inside the bag until everything's equal. So the next thing is hypotonic, right? So I'm placing the bag into a hypotonic solution. And so we place that in right here, and so the particles outside are lower than the one inside. So the particles will diffuse outward, and so until it's all even. So just a few facts about cell membranes. Cell membranes have a phospholipid bilayer, right? So it's kind of like this one I was showing you over here, right? It's kind of like this. It creates a barrier. Phospholipid bilayer, phosphate heads, which are hydrophilic. So let's break this word down. Hydro just means water, philic means attraction. So these phosphate heads like water. And then lipid tails that are hydrophobic, phobos is fear, and then once again hydro is water, so they fear water, or they don't like to be near water. So it allows hydrophobic lipids to pass easily. And then, so just to give you a quick demonstration of what that would look like. So you have your phosphate heads, right? And your phosphate heads, and then you would have your lipid tails, right? Like this. And so the main point is, and then you have your water, right? You have your water inside and outside. So H2O, H2O. Sorry, I'm writing really fast. And so what happens is you have your phosphate heads that like water, hydrophilic. So these phosphate heads like the water, so they'll be facing outwards and they'll be facing inwards. And so the lipid tails, right? They don't like water, so they'll actually face each other, and that's why it creates this structure. And so this actually allows hydrophobic lipids to pass easily, right? Because it's like this, H2O can't go through because it can go through the lipids on the inside. However, a lipid can easily just travel through because all of this is lipid. And now, but the thing is, you do need water to go in and out of a cell, and so the special channels that allow water to do that are called aquaporins, and they're just integral membrane pore proteins that selectively pass water through the membrane. So there are special proteins that allow water to travel in and out of the cell. And the final concept I would like to talk about is just hydrated ion size. So we have those ions in like a resting membrane potential and in neurons, such as sodium and potassium, but they're rarely just on their own. They're usually hydrated because they're in solution, right? Hydrated just means that water is attaching to the sodium or potassium. So what we should talk about is what happens to the ion size when it's hydrated. So smaller diameter ions have a stronger force. So they will be larger when they are hydrated. So without hydration, you're going to have just sodium, right, like this, right? And then potassium is bigger. You can see this on the periodic table. Stuff that's lower, for example, potassium is lower than sodium. it will be bigger than sodium because it just has more electrons in its valence shells. However, when it's hydrated, since sodium has a smaller diameter, it has a stronger force, right? And so since it's stronger, it will attract more water, and so it will actually become bigger than potassium. And so that'll be more useful as you go through the semester and you learn about selectivity filters in neurons and stuff and what allows it to pass through. And just the final thing, what allows the resting membrane potential is the sodium-potassium pump. And it's just a protein. You should be familiar with this. It's just 3 sodiums out and 2 potassiums inward. And it's active transport because it uses ATP. So that's just a basic review of stuff you'll need for neurophysiology. So I hope that helped, and thanks for watching.